Good afternoon, everyone, and welcome to the webinar on stability systems for light steel framing. My name's Andrew Way, and I'll be presenting the webinar to you this afternoon, or for the next 45 minutes to an hour. So firstly, welcome to everyone. This webinar is open to all, so open to not only SCI members, but also non-SCI members. We do have member-only webinars, but this isn't one of them. This is open to everyone. My name's Andrew Way, as I said, and I'll be presenting all of the material today. I am based at SCI. I'm an associate director here, and I'm sitting in the SCI offices as we speak. Thank you very much for joining. Just to give you a quick run through on what we are going to cover in the next hour. Obviously, we're talking about stability systems for light steel framing, so we'll be explaining what different stability systems are typically used in a light steel frame building. We'll be talking about some of the specific issues related to diaphragm action and racking resistance, which is becoming more common, I would say, and that's one of the main reasons we produced this new publication, P437, is to actually get some guidance out there about how to design for racking resistance and diaphragm action of boarded light steel frame walls, because it's something that's not covered in design standards or British standards or even European standards in that very specific application with light steel framing. As well as that quite technical material, we'll also be looking at an introduction to light steel framing. So I expect we've got a whole variety of people in attendance on this webinar. Some of you will be very familiar with what light steel framing is and what it looks like. Some of you may not. So we'll have a quick introduction to that as well. And we'll also be talking about some of the fundamentals of stability systems and stability requirements for steel frames. So we'll cover as much as we can throughout the hour that we've got. Obviously, we haven't got a lot of time to go into what can be quite a detailed subject, but there is the publication, and later on in the year we will also be running a more in-depth course spread over a couple of days, so a couple of hours each day on the same material. So if that's something you want more information on, then obviously that will be available from SCI as well. I should mention the publication itself hasn't quite hit the streets yet. Probably in the next week, maybe 2 weeks, it will be out there. So look out for that. But really, that is the basis for this webinar today. So in terms of applications of light steel framing and how that might be used in real projects. So light steel framing, as it says on the slide there and shows on the slide there, can obviously be used for housing, can be used for multi-story, multi-occupancy dwellings and similar types of buildings. Anything up to sort of 15 stories can be built with light steel framing as the primary structural system. And so it's mainly residential, but it can also be similar types of buildings that have got multiple internal walls. So maybe school environments, hotels, some offices, and also healthcare buildings as well. So those are the two that we're really talking about, and those are the main focus of the publication. But also light steel framing and cold formed light steel members are used in modular construction. So much of what we talk about can also be applied to modular construction, although there will be some slight nuances that mean it's a different sort of application for modular construction, but there's obviously a large degree of crossover. And then not in a primary structural usage, but a very common usage of light steel sections and cold form members is infill and external walling systems. So that bottom right diagram that we've got there, we've got an external wall system with light steel sections. In terms of the types of section profiles that we're talking about for all these applications, so commonly we're seeing light steel sections which are lipped C sections. Sometimes the web may have an additional profile, so you may have an indented web as shown there, or more commonly the plain Cs with a lip on the top flange are what you see most commonly. The lips in these particular diagrams are quite small, so you might actually expect to see a larger lip than is shown on those diagrams. Obviously, we've got typical section depths, which vary greatly depending on the application, but a wall stud maybe 90-ish to around 100, 120 in terms of depth. The gauge, anything from 1.2 up to 3 millimeters, obviously depending on the resistance required for the particular stud. So of a multi-story building, you'll have higher gauge studs towards the bottom and lighter gauge studs at the top stories. You may also change the spacing of those studs, which would be typically maximum, well, a maximum of 600, could be down to 300 millimeters, and they can obviously be placed in pairs back to back as well if the structural arrangement is such that that is needed. In terms of floors, with light steel structures, floors are commonly light steel joisted floors, or also composite slab floors supported on light steel frame walls are common these days as well. And where we've got light steel joists, they may be 200 to 300 millimeters deep, but with the smaller sections, so maybe only 75 deep or something like that, you can use those to make floor trusses as well. So all sorts of options with this technology. So here's just a few images which I like, and I think they show the overall sort of system of light steel framing pretty well. So on the left hand side there, we've just got some light steel vertical sections, obviously wall studs. Also got some cross bracing shown there, and we'll be talking a lot more about cross bracing throughout the webinar. And some light steel, I think in this case they're actually roof joists rather than floor joists, but very similar application. The next image shows decking being placed on light steel walls, so obviously there's going to be a composite slab floor in this particular development. We can also see some sheathing board being placed on the external walls of this light steel frame as well. And we'll talk about boards a bit more later on as well. And then the final image is just some, well, almost complete blocks. I think these are actually for some student accommodation. I should say that these images are not all from the same project. They're all from different projects. But obviously they'll show light steel framing in their various stages of completeness. So hopefully that gives a bit of an introduction to what we're talking about in terms of light steel framing. We're now going to move on to talk about some of the fundamentals of stability and stability systems and what they're required to do. So some of this will be very familiar to a lot of you, I'm sure, but it's worth going through just to explain the background for some of the stuff that's coming later. So obviously we have a structure, whether it be a light steel frame or typical multi-story hot rolled steel frame, those connections between the horizontal and vertical elements are nominally pinned connections. So if we don't have any bracing system or stability system, then effectively we have a mechanism, and if we apply some lateral load, then that structure can simply collapse and fold up. So we need something to provide stability. So in this publication and this webinar, we've referred to them as stability systems. In many cases, it will be diagonal bracing, but it isn't that in all cases. So we've taken the option of using a sort of a more encompassing term of stability systems, and we'll talk about different types of stability system a bit later. But in this diagram, we've got that indicated with some diagonal cross bracing. The diagram itself doesn't show all the verticals that you'd find in a light steel frame. As we saw earlier, you'd have verticals at sort of every 600 millimeter centers, so a lot more than shown in this diagram, but it indicates the purpose for what we need it for. So the bracing and the stability system obviously needs to be able to transfer horizontal and vertical loads sort of safely down to the foundations without causing the structure to collapse, obviously. And to do that, we need both vertical stability systems and horizontal stability systems, so we can transfer the loads to where we have the actual bracing or whatever it may be in terms of providing that stability. So in terms of the fundamental requirements, the first one we've got there is to be able to transfer the loads, as I've mentioned. So that is an ultimate limit state requirement for the safety and strength of the building, if you like, making sure that that is going to remain stable. We've also got serviceability limit states to consider. So we want to be able to control the horizontal deflections of the structure. We want to make sure that that structure remains usable and suitable for the intended use. So we want to make sure that we don't cause sort of discomfort to occupants with excessive deflections, or we want to make sure that we don't cause damage to internal finishes or external finishes for that matter with excessive deflections of the structure itself. And also there's a third requirement, and that is in terms of the frame stability. We want to make sure that any second order effects are taken into account in the design if they are significant. So we need to make an assessment of those second order effects to determine whether they are significant or not. And certainly if they are significant, then we need to make sure that those effects are taken into account in the design. And so that is also an ultimate limit state design case for the safety and the stability of the overall structure. And we'll have a look at that in a bit more detail in a few slides' time as well. So one of the main things is obviously what lateral loads are we dealing with? So we're obviously thinking about wind loads. We're talking about design within the UK in terms of the scope of this publication and this webinar. If we were designing in seismic zones, we'd also have seismic horizontal forces to consider as well. But we're not thinking about those sort of things today. But we're certainly talking and considering wind loads, but that's not the only horizontal load we need to consider. We also need to think about equivalent horizontal forces. So EHFs, if you like. These are defined in the Eurocodes, and in particular Eurocode 3 part 1.1. So Eurocode 3 part 1.1 is the base part of the Eurocode for steel structures. Light steel framing and cold form sections would be designed to Eurocode 3 part 1.3, but anything relevant from Eurocode 3 part 1.1 must also be taken into account for the design of cold form structures as well. So certainly equivalent horizontal forces are applicable to light steel frame buildings, and these are really the horizontal forces, or equivalent horizontal forces obviously, that would result from initial imperfections of the frame. And so there's an expression there given in the Eurocode that tells us how we can calculate the equivalent horizontal forces. So it's a factor, psi factor, multiplied by the vertical design loads, and then the psi factor itself has several terms which can be calculated as well. So in many cases, the alpha h and the alpha m values are simply taken as 1, and then we have a 0.5% or 1/200 taken as the equivalent horizontal force factor. That doesn't necessarily need to be done, and particularly for light steel frames, it's probably quite a conservative approach to just take the 1/200 and the other factors as 1. So in terms of the alpha h, it's actually given as 2/√h, where the h is the height of the structure. The alpha m is related to the number of columns that are stabilized by the bracing system, and columns is the term used in the Eurocode, but in terms of light steel framing, we don't have columns as such. We have vertical studs, but for columns we can read vertical studs. So one of the aspects of light steel framing is if you've got many more verticals than you would have in a sort of traditional hot rolled steel structure. So this alpha m value is reduced. If we just look at a graph of where we've plotted alpha h or alpha m and how they change with and the number of columns or the number of verticals and the height of the structure, then we can see that very quickly those two alpha factors sort of plateau out to a particular value. And so we should take advantage of that when designing our light steel structures, and we can use a reduced value for our equivalent horizontal forces. So this table, taken from the forthcoming publication P437, gives some simplified rules or some simplified values for the global factor that we can use. So instead of using the base factor of sort of 0.5% or 0.05, we can use a lower value. So these values in the final column, depending on the number of verticals and the height of the structure. And you can see that as we have a higher structure, so 3, 6, 9, 12, obviously representing 1 to 4 stories in sort of rough terms, and the number of columns. So any light steel structure is going to have sort of greater than 10 verticals. So if we had a 4-story structure or a structure greater than 12 meters in height, we're effectively halving the factor that we can use to calculate our equivalent horizontal forces. So that is something that's useful, meaning that we don't have quite the same value or quite as much horizontal force to design our systems to resist. I think obviously the dominant force is the wind load, but this is still an advantage that we can take advantage of. As well as those equivalent horizontal forces, which are a result of the initial imperfections, we also need to think about second order effects. So these are something different to those equivalent horizontal forces, but do also result from, in this case, not initial imperfections, but movement due to horizontal forces being applied. So If we've got an idealized structure on the left-hand side, all nice, perfectly vertical, but then we have some wind load, we still have the vertical forces being applied, but now they're no longer being applied to vertical columns. Even if we didn't have any initial imperfections, they're being applied to deformed columns due to the lateral load, and that leads to these P delta or second order effects. And whether or not those second order effects or P delta effects are significant or not will depend on several factors. Obviously, the magnitude of the P and the delta will determine whether they're significant or not, but they also depend on whether they're significant or not relative to the initial or not the initial, but the first order deflections or first order effects, if you like. So this image here is showing that whereas in the idealized situation we had a vertical load above the column base, here we've got it offset, and therefore that column base, if you like, is going to be subjected to additional effects, in this case shown as a moment, but there'll be other effects in the structure from these movements after the first order effects. So in terms of the assessment to determine whether these P delta effects are significant or not, again, the Eurocode 3 part 1.3 tells us exactly how we can do that. And it's all dependent on this alpha crit value, and alpha crit is dependent on our horizontal design effects and our vertical design effects, and importantly that story height and the deflection that we get within that story height. So the difference between the base of the column, if you like, to the top of the column, that horizontal sway is dependent on, or that our alpha crit is dependent upon those factors. Now we can calculate an alpha crit for each story of the structure, and then we would look to see which is the lowest value of alpha crit that we obtain. Typically that's often at the lowest story, but it might not be, so each story needs to be checked. And then dependent on the value of alpha crit determines whether or not we can ignore the second order effects or whether we can't ignore the second order effects. So if alpha crit is less than 10, then we cannot neglect those second order effects. Obviously, if it's greater than or equal to 10, then we can ignore those second order effects, and we can just work with our first order forces and moments. If it's between 10 and 3, then we can use an amplification factor to account for those second order effects. And if it's less than 3, then we must carry out a second order analysis to properly account for those second order effects. So those are all things that we must do in terms of the sway stability calculations and looking at things in terms of the ultimate limit state. In terms of the serviceability deflection limits, the Eurocodes themselves don't actually give deflection limits applicable to frames. The UK National Annex for Eurocode 3 part 1.1 suggests a height over 300 deflection limit for each story. However, it does also recognize that there will be cases where that H over 300 limit is not applicable or not suitable, and other values may be used or should be used. So in actual fact, we've got a different value in P437, and this is consistent with older SCI guidance, and it's actually H/500 as the recommended deflection limit. There are a few reasons why we do this, or why we recommend this. Firstly, that it then allows for the use of diaphragm action from boarded walls. So that's something that we'll come on to in a few slides time, but that H/500 limit is quite important for that, to make sure we don't get excessive deflections with those boarded walls. When it's not a purely steel system, so we've got some other materials that need to be taken into account with the board materials. When we're looking at X bracing, we'll see that the actual deflection limit is not critical, so it doesn't really matter what we take for the deflection limit, because it's always going to be the ultimate limit strength of the X bracing that actually controls the design. So whether it's H/300 or H/500 for X bracing, it doesn't really matter. And then also, because we've taken a stricter deflection limit, it also allows for the combination of different types of stability systems more readily. So where we might be combining the racking resistance of sheathing board on the external walls, and internal walls have X bracing. If we stick to this H/500 limit, then it's more conducive to actually using a combination of systems. So what systems? I keep talking about systems and stability systems. What are we actually talking about? So in terms of vertical stability systems, there's X bracing, obviously, and I've got a few diagrams and slides on that coming up. We've got integral bracing, which again is steel-based diagonal bracing, if you like, but a slightly different form. There's the diaphragm action or racking resistance of walls, and I will obviously go into more detail on that. But also you might have within a light steel frame, you might have a concrete core, or you might have a hot rolled steel frame providing some sort of bracing within that structure. Or of course you might have a combination of all sorts of vertical bracing systems within a structure. So various things to take account of when you do have a combination of systems. If you've just got one system, then it's much easier to carry out the design checks, but of course it's possible to use a combination. We also need to think a little bit about horizontal systems. So the vertical bracing systems are going to be positioned at specific points. We'll see that they are quite widely distributed, but they're still at specific points. So we need to make sure that we've got a good floor diagram and roof bracing to ensure that loads are or can be transferred from the point of application to the point of resistance in terms of these vertical bracing systems. So having a look at that in a bit more detail, firstly, the sort of the black and red diagram is a plan view of walls within a load-bearing light steel frame building, so a plan view, and the red lines indicate where we've got braced walls. The black lines are indicating there's still vertical load-bearing walls, but they don't have any sort of bracing in them. And then the gaps are obviously where we've got doors and windows and that sort of thing. There's also a grey area there, which is the lift and stair area, so that may or may not be of a different form of construction. Perfectly acceptable for that to still be light steel framing with X bracing where it can fit in. So obviously with X bracing and any sort of bracing in the wall, it's only going to work where you've got solid wall. So where we've got doors and windows, obviously we can't really provide bracing or stability systems in those locations. But as you can see, the red is widely distributed over the plan footprint of the building. It's not just in a couple of corners as it might be with a hot rolled steel frame structure. It is widely distributed. And we can also see from the diagram on the right hand side that across the elevation, the X bracing is also quite widely distributed, or can be widely distributed. It doesn't have to be like this. This shows various sort of forms of X bracing where we've got overlapping X bracing, we've got individual edge X bracing where it's not overlapping. And in this case, it's sort of offset from each other. You can have the X bracing sort of stacked one story to the other. Whichever approach is used in a particular structure, you need to make sure that the loads are properly transferred, and you design the members below and above each story for the forces that are obviously transferred from the X bracing. At the end of the X brace panel, you'll have additional axial loads in those end members. Some systems or some designers like to spread those around so you don't get a large accumulation at the base of the structure of accumulated vertical loads. Others preferred to have them stacked, so you can just design a holding down detail for that accumulated load at one specific point. So different solutions are used by different manufacturers and designers, but obviously they're all acceptable, provided they are obviously designed based on their actual arrangement. So the X bracing itself, typically flat strap. The edges of the straps may have slight profiles to try and keep them straight, because one of the main things with the flat strap bracing or the almost flat strap bracing is to avoid any slackness between the joist, or between the vertical studs when it's fixed. Obviously, because it's flat, it only has resistance when subjected to tension. It has no compression resistance to speak of. So we want to make sure that it's installed as flat and as taut as possible, because the panel will sort of deflect slightly to take up any slackness, and therefore you'll have additional movement if you do have excessive slackness. So there are various ways that, again, different systems use to avoid that slackness, whether it be a slight profile on the edge of the bracing strap, or it be tightening devices within the length of the flat strap, or it may just be the installation procedure itself includes a method to ensure that you don't have any slackness. Within the publication, and just shown here to indicate really, we've got various expressions and diagrams used and presented for different arrangements, and then formulae within the publication presented that you can use to design cross bracing. As I've said, the various design checks you need to carry out are obviously based on the tension resistance of the strap, the connection resistance at the ends of the strap. We've also got methodologies for calculating that horizontal deflection of that braced bay, if you like. And one of the things that can be important, depending on the level of vertical load, is also holding down details at the base. So obviously when you have that diagonal, you have additional vertical or additional axial loads within the end columns, which can obviously lead to uplift at the base, depending on your level of vertical load being applied to the panel. And that must be taken into account, as well as the additional vertical loads, which can obviously be accumulated, as I mentioned, from bracing in stories above. So here we've got just a simple example, obviously not showing all the calculations and everything, but we've got a braced bay with a 80mm wide strap, 1.2 gauge. So the strap itself has a tension resistance of 36 kilonewtons. The connections, based on 5 fixings at each end, have a resistance of 17.3 kilonewtons, which gives an overall resistance for the panel to a horizontal load equal to 12.6 kilonewtons for the ultimate limit state. And we've calculated that if that horizontal deflection is limited to h/500, then that capacity for that panel would be 10.7 kilonewtons at the serviceability limit state. So you can see there the ultimate limit state is slightly higher than the serviceability limit state resistance, but not a massive amount. And obviously the design load at the ultimate limit state will be significantly higher than at the serviceability limit state. So in this case, we can see that it will be the ultimate limit state that will be critical. The next form of steel-based bracing that's used with light steel framing is integral bracing, sometimes referred to as K bracing or W bracing. And you can see from the photographs there the different forms that it may take. And instead of using flat strap as the diagonals, this uses the same section size as is used for the vertical C-section studs, but placed obviously within the depth of the wall panel at various angles to make trusses, mini trusses if you like. And you can do that in various forms, again, as sort of shown on those photographs. If the ends of those members are swayed to become narrower at the ends, then they can fit within the depth of the head and base tracks. That's obviously the sort of like the neatest form of construction. You can also use gusset plates to form the connections. That often, causes a slight rise in the surface of the wall panel at those connection zones, so can make fitting boards a little bit more difficult. But if the right screws and that sort of thing are used, then it's not too much of a challenge, and you may have resilient bars and things like that to offset the boards from the wall anyway. The good thing about integral bracing is that it can be fitted within a narrow width of wall. So as you can see, it fits between the studs, so it can fit within a wall width of 600 millimeters, whereas the X bracing needed a much wider solid wall without an opening to be used. So this is more commonly used around windows and that sort of thing. And again, you've got the various design checks that you would need to carry out on panels with X bracing, so that the axial loads within the various members themselves can obviously be calculated, the connection resistance, and more so with these types of connections is the holding down or the uplift condition at the base of the bracing. Because it's over a narrower the width, then you'll get a higher vertical uplift or potential uplift force at the end of the bracing. And again, just for a quick example for you, we've got a panel here with this case has actually got a window in it or an opening in it. So we can see the integral bracing panels either side of that window. We've got the stud capacity or the section capacity of the short lengths of integral bracing at 65 kilonewtons, so that's not going to be a critical factor. We've got connection resistance, in this case of 10.8 kilonewtons, which gives us a complete panel resistance of 12.6 kilonewtons, so not dissimilar to what we had for the X bracing, but we've got a lower resistance at serviceability limit state. So these are sort of more flexible than the X bracing because they're over a narrower width. So in this case, it is the serviceability limit state that is the critical case, and also the design of that anchorage detail at the base of these integral bracing locations. So those are the two types of sort of steel-based system with light steel framing. You'll also have the potential to use racking resistance from boards. So as I said, this is one of the main reasons that we really felt that a publication was needed, because there wasn't the guidance available in the depth required by many of the um, the warranty providers for light steel or for new build residential. We often got lots of questions about how racking resistance can be used and how it should be tested, and then how you design or come up with design values from test results and that sort of thing. So we've been through the process of detailing that in quite some detail in the publication. As I said, there isn't anything in terms of design standards or Eurocode or British standards for light steel framing. There is for timber-based frames, but timber-based frames are not exactly the same as light steel framing, particularly the way the fixings are used, the way the fixings are anchored within a timber stud compared to in a thin gauge light steel frame. They all give different sort of fixing stiffnesses, if you like. So that does need to be taken account of and derived from testing. It's still within the scope of the Eurocodes, because most of the parts of the Eurocode, so Eurocode 3 part 1.3, and the basis of all Eurocodes, Eurocode Nort or EN 1990, they all allow for design assisted by testing. So that's what we're utilizing here. We're carrying out some testing, and we're deriving design values from those test results using Eurocode methodologies. Some general points about what you find when you do the testing. Firstly, it's that the deflection case is the critical case for braced wall or for boarded walls. So you get a very high ultimate limit state resistance, typically 2.5 times the serviceability limit state resistance. Obviously, the where the boards are fixed to the frame, you get the highest fixing forces at the corners, but then as those fixings fail towards the end of the test, then forces are redistributed to other fixings around the perimeter of the board. So it's quite a ductile failure, or quite a long tail to the force deflection curve that you get from these tests. And that leads us to the next point there, that the ultimate limit state of these resistances of these boarded panels is limited to a maximum of 60% of the test failure load, to make sure that we are within the elastic range. But because it's the stiffness or the deflection case that is the critical case, it's really the calculation of the stiffness that is the most important thing from these tests. And the stiffness is calculated at a value between 20% and 40% of the maximum force obtained during the test. And then the ultimate limit state stiffness, which is required for that second order calculation and P delta an alpha crit calculation, is taken as 0.7 of the serviceability limit state stiffness. So obviously this has gone into in a lot more detail in the publication, just trying to provide you with a few highlights and bullet points here. The test methodology follows that of the timber frame structures, so this EN 594 test standard. The base anchorage needs to be adjusted slightly to what is described in that standard to suit the light steel frame panel, but otherwise it's the same methodology is used. The tests can be carried out with or without vertical load applied to the panel, but basically it's a panel that is then subjected to a horizontal load, and the deflections are measured along with the level of horizontal load that is applied. You need to carry out a minimum of 3 tests to make sure that you can judge the variability that you get, and then you can carry out statistical analysis on those minimum of 3 tests. Obviously, the more tests that are carried out, the more reliability you can place on the group of tests. So this shows an idealized sort of plot that you might get from a test. In reality, you get a much longer tail to that test than is shown in that diagram, and it shows you how to calculate the stiffness. It's simply obviously the slope of that output between the 20 and 40% applied load values. And then calculating the design values is following the Eurocode methodology and that of Eurocode 1990, and it's given in Annex D. So I won't go into this in too much detail, but there's a slightly different approach for the design resistance and the design stiffness. Both of them, you effectively calculate the mean result from your tests, and then you subtract a number of standard deviations from your results to come up with a design resistance or a design stiffness from that set of results. Again, this is a table from the publication, and these are the number of standard deviations to subtract depending on how many tests have been carried out. So this next slide, it shows some sample data, just some fictitious data. So we've got 4 tests, and we've got a failure load from each test, and we've got a stiffness from each test. Obviously, a mean value from each group of tests for those values, standard deviation, measure of the variation of coefficient of variation, and the Vx known is the number of standard deviations. So that's coming from this table here, based on the number of tests, which in this case is obviously 4 tests. And so calculating the design value, so the design resistance, fairly straightforward. In this case, we're getting 26.2 from a mean value of 27.8. And the stiffness, we're getting 1,617 from a mean value of 1,664. So obviously there's a reduced value from the mean, and you can't simply use the mean as a design value. You need to take into account the variation that you get from test results. In terms of using that data, obviously the ultimate limit state resistance of 26 kilonewtons, that's directly applicable to a panel of that size. If you want to think about the stiffness and how that relates to a applied load, well, obviously you can multiply that by the deflection limit. So H over 500 gives us 4.8 millimeters. So we actually get 7.8 kilonewtons. Or if you want to represent it another way, 3.2 kilonewtons per meter width of panel. So in this case, obviously you can see SLS will be critical case. In the publication, it goes through how to apply those design values for different situations. Obviously, you've tested a panel which is commonly 2.4 meters square. In reality, you're not going to have exactly the same width of panel or height of panel, so you need to adjust for that. You also need to adjust for the level of loading. So provided that the design vertical loading is greater than or equal to the test loading, you can use the same values. There is a methodology for using or adapting those results for different types of boards or different fixings, and that's some small scale shear tests, and I'll show you what they look like in the next few slides. And adjusting for panel sizes, so obviously the width or the height may be different, and the number of boards may be different, which is crucial because of obviously the board perimeter is where much of the highest level of loads are experienced by the fixings. So again, we've given some hopefully useful information in the publication, repeated here. So we've got a theoretical expression, but we've got, excuse me, some factors. So if we're starting off with a 2.4 by 2.4 panel, then we have a factor of 1 that can be applied to the stiffness. If the panel height increases, then the stiffness factor reduces. If the panel width increases, then the stiffness factor increases, but it's not a linear relationship. So this is quite useful to use, and that is the expression in one of the appendices in the publication. Sorry, in the publication explains how that is all carried out. So the actual use of boarding is quite interesting, and we get lots of questions about that. Obviously, where we're using steel stability systems, that's generally accepted, but obviously the questions arise about the robustness and durability of boards subjected to loads sort of throughout the life of the building and that sort of thing. And obviously wind loads blow in different directions, so you have loading and unloading cycles on this boarding, and how that is all taken account in the design methodology. So one of the key things that we've included in the publication is this point about accidental load case, and we have said that because events such as water damage can cause loss of structural performance from boards, so it's unlikely that you're going to get widespread flooding, although obviously ground floor you might get widespread flooding of a structure. Other locations you could obviously get localized flooding from leaks and that sort of thing, but it's unlikely to be widespread throughout a structure. But we have said that you should carry out an accidental load case check. So this is designing the structure and the stability system under the accidental loading load factors, and checking that you still have a stable structure where the contribution from any boarding that would be impaired by an accidental event, which could be flooding, should be neglected. So that's a key part of that. So that's it, sort of a long-winded way of saying that you shouldn't be relying entirely on boarding to provide vertical stability. And then we've also got these small-scale tests that are included within the publication, and these are to carry out. Well, there's two purposes for carrying out these tests. Firstly, to determine the performance when subject to cyclic loading, and also to determine the performance of alternative boards and fixing arrangements. So you may have carried out some large panel tests, but decide you want to use different fixings or a slightly different board. Instead of having to carry out those tests again, you can carry out smaller scale tests and determine the results, or from the results determine the change in performance that you would have got with a large scale test. So you can see the general arrangement. We've got boards attached to either side of some light gauge steel, and we apply a vertical load. There's a gap beneath to allow the load to be transferred through the fixings to the board, and to determine some resistances. Those are the sort of dimensions and everything that we've included within the publication. It's possible to, these are shown as solid board pieces, but you can also include joints whether they be horizontal or vertical, and position the fixings nearer the edge if you want to examine the behavior of fixings near the edge of boards, for example. But the loading arrangement for these tests is quite important, and obviously you can see here that it's a cyclic loading, so we load up to sort of a 10% of the expected failure load. I should have highlighted from one of the previous slides that the first test is a complete test to failure, so you've got a good indication of your expected failure load, and then a following minimum of 3 tests you load up to 10%, then load up to 40%, and then you carry out 10 cycles between 10 and 40% of that expected failure load, and then test up to failure at the end. And to determine whether the board that you're using is suitable for racking resistance in this structural application, the condition is that the stiffness obtained from that 10th cycle should be greater than or equal to the stiffness obtained from the very first cycle of that cyclic loading. So for the first and the last cycle, you can determine that the stiffness from your results and make sure that that condition is satisfied. Obviously, what you want to achieve is to make sure that you don't get a reduction in stiffness with more cycles of loading. There's a little bit about combined systems on that slide there. Obviously, more detail in the publication, and I know we're getting near the end of our time. So combination of different bracing systems obviously needs to consider their distribution and the differences in their stiffnesses to determine what loads they will be subjected to. And there's lots of other good stuff in the publication which I haven't had time to go into in detail, obviously, in this webinar. So things like sliding and overturning, floor diaphragms, etc. You can see the list there. And of course, there's lots of example calculations in the publication as well. So that brings me to the end of the material. I'd like to say that the publication itself is coming out, as I say, within the next 2 weeks. A big thank you to all those who funded the publication, which is essentially the members of the SCI Light Steel Forum. So that's lots of light steel frame manufacturers putting in to contribute to this publication, which will be a benefit to the whole industry, not just the members of that Light Steel Forum. So very much thank you to them, and those are obviously acknowledged in the publication. Also want to bring your attention to the fact that SCI TEDS modules are currently free to download and use until the end of March. Normally these are something you would pay for, but until the end of the financial year, those are available to download and freely to use. So if you want to look at that, you can follow that QR code or go to the SCI website. And also to highlight what's coming up next in terms of SCI courses and webinars. So start of March, 5th of March there, we've got how to design using less, presented by our CEO, Graham Couchman. And then the next course we've got is Steel Connections design course over 4 parts, presented by David Brown, who's a regular presenter on many of our courses. So thank you very much for listening. I will now have a look at the questions to see what we've got. It looks like we've got quite a few questions, so I'll see which ones are most relevant to answer now. So just bear with me a few minutes. So first question is asking whether story-to-story module uses a pin connection. So I think in most cases, module-to-module connections would be considered as a pin connection, yes. A question about whether you can interpolate between psi values. You can interpolate between the psi values, but also the expression is given, so you can calculate exact values as well. Got a question about the use of staggered bracing, and how the loads, asking about how the loads should be distributed between those staggered bracings. So yes, I think this is, I was talking about transferring loads from bracing systems between stories. Obviously that loads need to be transferred down to the foundation, but obviously at the floor level you do have a stiff element, whether that be a floor slab or an edge member and a top and base track. So some of that horizontal or some of that vertical load can be transferred horizontally to sort of studs either side. And so there is some guidance in there about what's acceptable on that. There's the question asking about whether boards can be used for stability. So I think I've addressed that with some of the later slides in the presentation. General question, or a specific question, but it's generally about distributing loads to different stability systems. So yes, you need to look at different stiffnesses of those stability systems and determine, and then distribute loads in proportion to their stiffness. So that was like one of the later slides that I had in the presentation. There's a question about deflection limits. I think this question is getting confused between the sort of sway deflection limits and then the out of plane deflection limits that you might have on a wall panel itself. So wind blowing on the face of a wall panel and that deflection limit. So not particularly related to the stability system, but there's guidance in SCI publication P402 about that. The tightening strap, or the tightening of the bracing strap, there's a question asking about the details of that. Those devices are sort of proprietary solutions by different manufacturers. So I'm not really at liberty to divulge those, but yeah, if you look at certain websites, you may come across them. So yeah, there's a question about the design of these stability systems, and something that I should have said in the webinar, obviously. These light steel frame systems and structures are generally designed by the manufacturers or someone working on behalf of the manufacturer. So the general practitioner, design engineer, will not necessarily need to know everything about how to carry out this design, because it's, as I say, carried out by the light steel frame provider. Obviously, if you're carrying out checks and that sort of thing for a third party, then this information is particularly relevant. And if you're obviously developing your own system and design methodology, then all of this information is particularly relevant. Generally, with light steel framing, preloaded bolts are not used. So it depends on the system, I say, but in many systems we'll use countersunk bolts within preformed dimples in light steel frame sections, so you don't really have the same clearance hole and movement with clearance holes that you would get with hot rolled steel connections. There's a question about limiting cracks during transportation. Yeah, certainly that is a significant consideration depending on the level of finish that you're putting on any preformed panels. Transportation potentially can cause cracks. If you're designing panels to meet this H over 500 limit, then I would expect that any cracking would be very limited, but it obviously depends on the transportation solution and the quality of the roads and everything like that. But in most cases, that is not the overwhelming critical condition. But if you're applying tiles and that sort of thing off-site, then some additional consideration might be required. Asking about the inclusion of windows within a wall panel. So usually the parts of the wall sort of above and below the wall panel are neglected in terms of providing any racking resistance, and it would just be the solid full height wall panels either side of an opening that you would consider when determining your racking provision. Yeah, I think the other questions probably a bit too much detail to go into. Lots of them I can see would be addressed by the publication itself. I've got a question: when can notional horizontal forces be ignored? I can't think of any occurrences when notional horizontal forces can be ignored. Yeah, so I think that's the end of the questions as can be answered now. So thank you very much for listening, and I will look forward to hearing any comments about the publication. So thank you very much.